Okay, this this video cast is to go through elements of what we discussed in the last lecture on molecular modelling. I've got the impression from some of you in the audience that you didn't follow what was going on, so I thought if I put something that you can look at your leisure and think about a little more, it might help the subject sink in a little. Okay, so here we got a desktop. Currently it's showing a Mac desktop, but that's immaterial. This would be the case on most PCs with the various bits of software that I'm going to show you installed. So where we're going to go first is we're going to go to this site, and the way that I've got there is by going to PubMed, to PubMed compound, and what we're going to put in the search window is dopamine, which I used as an example in the lecture. And this is quite a nice little search engine, PubChem compound, because you can find information about most bioactive molecules here. And here we've got a 2D structural representation of dopamine. But where I want to go is I want to actually take the smile string, which I introduced you to, and show you that you can do a file conversion on that smile string to generate a 2D structure from it. This is a package called JChemPaint, which is freeware on the internet. I think it's available on many platforms, but this is on the Macintosh. This is a Macintosh version. I think it's available to PC users as well. And what we're going to do is we're going to paste the smile string in that window, insert the smile string into the package, and you can see that we generate a two-dimensional structure here. And that demonstrates conversion of 1D smiles information into a 2D chemical structure. And we remember what we said about the 2D chemical structure is that is the lingua franca, the language that all chemists talk in to one another. What I'm going to show you now is that we can take that structure and get rid of it. And what I'm going to do is I'm going to demonstrate the construction of a drug-like molecule. I just so happen to know that this is a dopamine active compound. So this is active at one of the dopamine receptors. I can be very specific about the stereochemistry. Now, hopefully, what I'm going to show to you is that I can save that structure now as a smile string. In other words, taking 2D back to 1D if I wish. And if I just hide this and look for my desktop, here's the file. And I'm going to open that file in any old text editor. This is a text edit, and there's the string. Okay, so we've got that smile string from that structure that I put within the 2D package, thereby demonstrating that we can convert formats in both directions. Okay. So what I'm going to show you now is that we can take smiles information and in fact I'll take that I'll take that file back out because we can use that, and I'll open the text editor again. I apologize for that. Let's open that back up again. What I'm going to do is show that we can take that smiles information and convert it into 3 dimensions. I'm going to go somewhere different for this, and this is a NIH cactus which again is a freely available site. It's a chemoinformatics tools and user services site. And I'm going to open a Smiles translator. Now, the corporate world, the drug industry wouldn't do this. They would have all online facilities as part of their routine tools, but we've got to use open source software to demonstrate a similar sort of approach. So I've pasted the Smiles string from the structure that I put into the 2D editor. I'm going to select a PDB format, which is a protein data bank format. Now, the PDB format is a universal format for three-dimensional information. And I'm going to select three-dimensional information here, and I'm going to ask it to translate that file, and with keeping my fingers crossed, it's going to do that. It's saved a file, which has got a horrendous file name, but that's immaterial. And here is our file, appeared on my desktop. Now I can have a look at that file. There are various chemical viewing packages. This happens to be MacPymol, but Pymol again is available to educational establishments, academics and students alike. And then we have our 3D structure. That was the structure that we put into our two-dimensional program. And you can see that it's taken up, it's understood the aromatic ring and the hydroxyl groups. It knows that this six-membered ring is not aromatic, it's aliphatic. It's actually built the structure in a reasonably chemically sensible ring conformation as well. And within any viewing package, you can change the way in which the compound looks. We can do spacer filling models. That's actually quite a rough. Let's improve the quality of that. There we go. So that's actually quite a rough. That's the van der Waals surface of the molecule. So this is visualizing our three-dimensional information. But we don't want to visualize it. We want to do something sensible with it. So what I'm going to do is go to the molecular operating environment package that I showed you during the lecture. It'll take a while to load up because it's actually quite a big program. So I do apologize for this. It's taking an awful long time to load up, in fact. Oh, I know. I'm terribly sorry. That didn't take any time to load up. It's this one that I need to load up. Apologies for that. So I'm launching Mo now. There we go. And remember that Mo is a molecular editing and molecular mechanics, molecular dynamics software package for drug design, and will allow us to import our structure. I'm going to look for it on the desktop, and there's our PDB file that I read in, that I saved. We've got some options that we can select to bring the information in, but we're just going to accept the defaults. And our structure comes in. It looks somewhat different there, but that's because the Mo environment chooses not to show us hydrogens. So if I ask it to show all atoms, there we go. It shows all atoms. What you may noticed if you were watching very carefully is that when I showed the hydrogens, and it's been imported into the into the molecular modelling software, it's already decided to protonate that amine to take it to an NH3+, which is what would be chemically sensible for that drug. Okay, now remember what we mentioned before. If I show you what information is available, all the elements are in place. It understands that nitrogen is now an N+, so it actually understands that. And if I hide that but show you molecular mechanics parameters, and it's had a stab at the molecular mechanics parameters and assigned those to the structure, so it should be ready for molecular mechanics. Because it understands the atom typing, and from those atom types it goes away and looks up how a bond should work, how an angle should work, how a dihedral should work, and so on. Fills the force field components together, ready for that modelling to take place. I'm going to take that away and show you that the charges aren't there at the moment. So what we need to do is to prepare the structure and calculate partial charges for all the atoms. The force fields that are applied, we have different types of force fields and charge calculations that we can apply. Gastiger is actually a nice algorithm for calculating charges accurately, and it's done that. It's now calculated our partial charges. And remember I described to you what the partial charges are. You've learnt partial charges by using the delta plus and delta minus symbols within molecules to indicate dipoles, and all that dipoles are, bond dipoles, are a description of where the charges reside in the structure to describe the overall full dipole of the molecule, and the full dipole of the molecule actually is a balance of positive and negative charges across the molecule going in a particular direction. But if the molecule is a neutral molecule, the charge should integrate to 0. Okay, so now we're ready to go. Just to check that we can do molecular mechanics on this and calculate energies. If I do an energy calculation, you can see that I have a value of 51.3 here, and all of the components of the force field are being calculated there. You can run that in slow motion to have a look at that later. Now what I'm going to do is minimize the structure. Remember, these fragments are guesstimates of the positions that the atoms want to be in for an ideal molecule. What we're going to do is actually minimize the structure, and you see that there's a geometry change, albeit very small, which actually indicates that the 1D to 2D, the 1D to 3D conversion and then 3D into Mo has all worked very well, because it's quite happy about that minimized structure at this point. So what I'm going to do is I'm going to select a rotatable bond, and I'm going to edit the distance, and I'm going to calculate potential energy, and the energy, you can see, has gone up considerably. This is the one that we're looking at here. If I click here and recalculate the potential energy, sorry, let me just let that go away so we can refresh the screen. You can see that the energy for that bond extension has considerably changed. If I minimize the structure, you can see the bond goes back to a sensible energy. If I now a sensible geometry. If I recalculate the potential energy, that potential energy has now gone back to a smaller energy. Okay. What I can also do is illustrate that dihedral angles will cause the energy to change. You can see that it changed from the previous value to a higher value. I can minimize that structure. It's a different conformation that we're evaluating, and you can see that the energy's changed again. So that means that we can change geometry, we can change bond angles, bond lengths, and explore how the energy of the system, how the energy of the molecule changes with those potential energy of the molecule changes with those geometric changes. One of the things I said that we'd be interested in is how to visualize how the molecule might behave in real thermal motion, and what we can apply is a simulation called molecular dynamics. It actually looks quite complicated here, but basically the molecule is equilibrated at a certain temperature, and then it runs for, and these are picoseconds, so these are motions in the molecule that happen over 100 picoseconds, and warms up to 300, and then at 300 it runs for 500 picoseconds to see what the molecule does. And we're going to see how the molecule behaves under thermal motion. So this is molecular dynamics in action, and we can see that actually this is quite a rigid molecule, and at a reasonable temperature, which is approximating body temperature, the molecule is only just really jiggering around. You see the aromatic ring is bending a little bit, which is interesting, and in fact benzene rings do that in real life. The aliphatic ring is quite happy where it is, and that substituent is quite happy where it is as well. You can see periodically that these OH groups get, or this OH group gets close to that oxygen and interacts with the oxygen to give a hydrogen bond, and that's reported every so often by a light blue line. There you go, it's just appearing there. We're going to cancel the dynamics now, and that molecule is now actually warmed up a little. Look what happens if I do a potential energy on it. You can see that it's raised to 40. If I minimize the structure and then recalculate the energy, you see it's dropped back down to 23. Now that's effectively the energy it would be if you removed all the excessive motion in the molecule and chilled it down to 0 Kelvin. You've taken all the thermal energy away from it. So this is just a molecule that's got only potential energy as part of its structure. Okay, I hope that has explained a little more about it and given you time to think about it. Just think of if you haven't taken on the concepts too well, just think about it in broadest terms, that you can take chemical information in various formats to generate three-dimensional models of drug substances, and this is a small drug substance, into a molecular modeling package and model properties of the molecule. One thing we can also do while we're in here, which is quite cool, and this is what graphical environments allow us to do, we can calculate molecular surfaces on our molecule that show properties of the molecule, like charge at its surface. So if I just take that away, if I make that map a little transparent, you can see that the oxygens are very electronegative compared to actually the nitrogen's electronegative, but it's in this particular molecule the charge is not really showing itself at the surface. which is quite interesting. You can also get a sense of the shape of the molecule and its charge properties. We can demonstrate different properties like lipophilicity. So this is which regions of the molecule are likely to interact with lipophilic moieties within a receptor, and that's the green area, and that you notice we're hanging over the aromatic ring and the aliphatic ring, and which regions of the molecule are likely to interact with hydrophilic components. There's various other properties there that we can look at as well. If I was to calculate a interaction potential map, and this is how various probes, molecular probes, will see our molecule. I'll explain this later at a later lecture. So what we're going to do is create that surface. It takes a while to calculate it, and what I can, if I turn various things off, I can. How would a water molecule see that molecule in the most favourable place? Now, a water molecule is calculated to interact here quite close to the OH groups. That's what that map is telling us. If I was to broaden the search a little bit and say, well, I don't want it at this, so this is what's called an isoenergetic map. It links all the points at which a water sits in that volume. Each one of those intersections here, if I turn the map slightly, each one of these intersections is a point in space where a water can sit, and at the same energy, which is the energy of minus 5.5 kilocalories per mole, which is an attractive energy. If I make that energy larger, we pick up different sites where a water can sit. If I make it smaller, you can see that we narrow the points down to individual points within a grid. So Mo selected that to start to show where waters would like to interact. And you see, if you make it bigger, this is worthwhile doing, you can see that a water molecule will be attracted to each of those positions on those hydrogens on that electronegative element, and you can imagine the water would be attracted by its O towards these positive charges, and you can see that there are other ways in which water can see the molecule. Now, water can act as a molecular probe for functional groups on a receptor, like the OH group of a serine on an amino acid. It simulates how an OH would want to see this molecule, and it's useful for calculating positions within a receptor that a drug might want to go. So people use these grid maps to locate a molecule within a binding site, or at least to explore the ideas. So this can be used numerically in a mapping procedure to dock molecules into an active site, but it also can be a mind exercise. In other words, where would my molecule want to sit within a receptor because of potential functional groups that will see the drug a particular way. So that's quite a nice demonstration there. Just by accident I've chosen that molecule. And one of the benefits of molecular modelling is that we can overlay graphical information to enrich what we can do above and beyond what a real 3D model of a molecule would be able to do for us. Graphical environments within a computer environment, a modelling environment, allows us to look at virtual things and visualize things that can't be gleaned from a three-dimensional model. Of course, good medicinal chemists can see these things in their head. They have this sort of ability to understand where molecules will sit, but computer tools allow a novice to visualize these things as well. The one thing that's good about the molecular operating environment is it's got extremely good built-in help that's accessible, and it's well documented, so it can take users from a very low level to a very high level in a short period of time. So what I'm going to do is close that system now and show you that we can do the same with a more complex molecule, and I'm going to try and find a sensible structure to show you. So I'm now looking for a target molecule that will be interesting for you. So what we're going to do is open a PDB file that contains a protein. Now the good thing about Mo, well, it's actually double-edged, it's a good and a bad thing. This has brought a protein molecule into Mo. It's showing it in a cartoon format, so you get a sense of what the molecule is like, plus some individual information. And you can see that this molecule is not only a protein, we've actually got quite a complex cofactor. This is a flavine dinucleotide, adenosine dinucleotide. There's the adenosine, there's complex phosphate backbone, and there's the flavine. This is actually a redox enzyme that uses this chemistry of this centre to perform redox chemistry on its substrates. We can edit sequences, so I can remove anything that's not protein. You can see that now our flavine is gone. I can what I know about this protein, so I can do certain things to it and realise that I'm not doing anything so drastic. So I've edited the protein through a sequence editor, and here are the amino acids in our protein. And here is our edited protein. It's raw now, it's a protein. The cofactor's gone. It may be that we want the cofactor to actually do our modelling with, but let's just consider the raw protein at the moment. I now start preparing the molecule. The three-dimensional information that's come through the PDB database means that there are some things wrong with the structure. That comes from just errors within the 3D coordinates that can be experimentally derived. We can correct those problems within Mo, so it causes any errors to be corrected by an editing procedure. I can now decide on protonating the protein as it would behave within water at its isoelectric point. So all the amino acids that are acidic and basic exchange their protons to give a neutral molecule. By retitrating, it takes a while to do it. It will retitrate the amino acids, and if you look carefully, you may be lucky enough, if we go in close enough, you may be lucky enough to see reprotonations happening. So what happens here with this algorithm is it tries various combinations of partitioning positive and negative charges throughout the molecule, finds the best solution for that, and actually comes out with a solution of how the protein should behave at its isoelectric point in water. And now this protein is ready for action. It can do all the things our small molecule did before. So we can minimize it. So if you notice now, you can see there's some geometry changes happening, just like it did with the small molecule, the small drug. There's things trying to be sorted out by the molecular mechanics software that's taking the energy down to a lower value. And if we just concentrate on one part of the structure, we should be able to see some changes happening as the coordinates are updated. And you can see that the consequences for these coordinate changes is that our protein structure is changing its shape slightly. This minimization is really affecting side chains, because the side chains are the easily variable components in terms of conformation within the protein, as we mentioned before in the lecture. And you can see that the minimization takes actually quite a long time compared to our small molecule, which is what you'd expect. We've got more bonds and angles and dihedral angles and charges and van der Waals interactions to consider. So it takes us a while to get to a minimum energy conformation that's going to be a working structure. And you can see that the energy is now negative and favourable compared to a positive energy that we started off with, and it's actually working very much in our favour. So we don't have to wait too much longer. I'm going to cancel that minimization, and I'm going to show you what happens again with molecular dynamical simulation. And here is our protein under dynamical flux. The structure is being given thermal energy. You can see that the cartoons are changing as well. So you'll notice areas of red and blue. Red indicates alpha helical regions, blue indicates loops, and yellow ribbon areas. And you can see that structures fluctuate and change. So some elements will change into a, if you look at, I think that's, let's see if we can spot it here. We can certainly spot it around this area. Some coordinates are falling more into an alpha helix than they are a bend, and then the bend's changing back to more alpha helical characteristics. So that tells you that alpha helices, and particularly at the end of an alpha helical run, are a little bit fluxional. They move around. I'll just try and center this molecule. There we go. Now if you run that simulation for long enough, you start to pick up all of the potential motions that are available to the protein, which is the side chain movements, which we know it's capable of doing. You can see that we're actually picking up some tertiary structure element changes, like beta or sheet-like configurations going into helices or loops, and helices here turning into a loop and back again. You can see that the major loops are not moving so much. If you wanted to investigate that motion, you would have to run a simulation for a long time to start to pick up longer scale, time scale motions like loop changes. But these small changes which are occurring here are happening often enough that we pick them up, but more slower actions of the molecule take a longer simulation to spot major changes, and that takes some particular analysis tools as well to pick up those variations. You can do it visually, but you can also do it from statistical analysis tools. You know, where is the molecule fluxional and so on. So what I'm going to do is cancel the dynamics there. I'm going to take off the ribbon structure, if I can do that. I'm sorry, if I select the molecule and take the rendering off of the molecule, but show the molecule, show the atoms as a line structure, show all atoms. Here is our molecule with all its hydrogens on, much more recognizable colors, red, white and blue, so red oxygen, blue nitrogen, white hydrogen. And I can do various things with, I can color the atoms, show charges, sorry. I can color the atoms by element, something called B factor, how hot the molecule is. That is reflective of how it moves around in its crystal structure. I can color by chain. There's lots of things I can do graphically to the molecule to investigate its properties. But this now demonstrates that we can have a protein ready for molecular mechanics, and we can have a small molecule ready for molecular mechanics, and we can now interact the two together. The way that we would do that is I would open a molecule folder and read an appropriate file in. So I can show you where our molecule is, and we can now start thinking about how our molecule is going to interact with our target. But we'll look at those things at a later date, so we'll stop there.